Hi, we have a question which is water flow in and out of a device as shown in the figure there. Calculate the rate of change of the mass, which is dm/dt in the device. That means inside the device, which is control volume. Thus, from this case, we need to specify our control volume. So here is our control volume that consists of control surface. Thus, we have the flux term and the control volume term. So the first step, we have to identify what the question asks. Alright, the question asks, calculate the rate change of mass, which is dm/dt for the control volume, which is this one, control volume. So the first step, what we need to do is step number 1. We need to list out all the assumptions. What our assumption number 1, which is we consider that the flow of the system is steady. So d/dt of the system is steady, so it is equal to 0. Steady flow of the whole system, right? And secondly, this is the water. The medium of flow is water. Thus, the density is constant. And then the next one, we assume that the velocity crosses this pipe is uniform velocity. So we can use the average velocity at point 1, 2, and 3. And then we need to specify, this is, let's say, point 1, this is point 2, and this is point 3. Applying the Renault transport theorem, apply RTT, which is defined as capital D/dt end of the system, equal to local derivative d/dt at the control volume, right? Intensity property rho dv, this is volume, plus integral of control surface, which is intensity property rho v dot n product vector dA. The whole this is the Renault transport theorem to convert the system into the control volume. Alright, next we have to cancel out this term. Right, the change of system is equal to 0, since we assume the flow from inlet to outlet, the whole system is steady. So this one equal to 0, and this one we cannot equal to 0 because it is mentioned in the question. Calculate the rate of mass flow in the device, which is control volume. In the device, this is control volume. Alright, this is our control volume. So from here, we expand this, the term here, and as well as this term. So from here, this is 0 equal to d over dt control volume. Alright, this is the intensive property. Remember, in order to get the intensive property, the extensive property must divide with mass. So this intensive property equal to extensive property divided with mass. So n here is given the mass. So mass divided with mass is equal to 1. Alright. Then we replace this one equal to 1 and we replace intensive property equal to 1. Leave it only. Density dV plus integral of control surface rho v dot n dA. From here, we need to expand further. Alright, since we use only the uniform velocity, thus the area can be reduced to area 1 and area 2 as well as area 3. So we know that this term, alright, this term is actually mass. Why mass? Remember that we have density equal to mass over volume. In order to get mass equal to density multiply with, alright, density multiply with volume. Thus, this gives the mass. So here is actually, we can replace this one with mass. So 0 equal to d m over dt of the control volume. This is for control volume. Remember the question asks the mass flow rate in the device. So control volume flow rate, which is mass flow rate in the device CB. Alright, plus this is flux. How many surface area across this section? This control volume. We have 1, we have 2, we have 3. So we have 3 components. So we need to add all the components. So component number 1, which is into the control volume. When the flux into the control volume, it is negative n. So here is negative n unit vector. This is out of control volume. This is positive n. And this is out as well, positive n. So we can replace this one, bracket. Right, bracket. We can replace this one with bracket. Alright, this one rho negative. Remember, this is n value. Rho velocity 1. This is rho 1, velocity 1. This is n is a unit vector which is equal to 1. Area 1. Plus point number 2. Point number 2 here is plus n. So rho 2 v2 a2. This is positive because out of the control volume. And point number 3 as well, out from the control volume. Plus rho 3 v3 a3. Okay. So from here, it is given that when we look at from the inlet, we need to draw our eyes. Okay, for example, this is our eyes. What we look at the cross-sectional area? Definitely, we look like the circle. So apply the formula of area, which is pi, given here is diameter, pi d squared over 4. Okay, this is area 1, diameter 1 as well. Fortunately, it is given that the mass flow rate 2 is 4 and the volume flow rate is 0.008. So we can actually replace the point 2 here is actually equal to mass flow rate. This term basically the equation of mass flow rate. Remember that we have derived previously the conservation of mass leading to the mass flow rate equation, and this one as well is the mass flow rate. However, mass flow rate at 2 given, but this one is not given. We can use the relation of mass flow rate with the volume flow rate, which is m3 equal to density multiplied with volume flow rate at 3. So here we can definitely get, we rearrange the equation. This one we move to other side, become negative dm over dt equal to this one negative rho of water, which is 1000. Velocity at point 1 is 10 meter per second. And the area here, we use the formula pi d squared. Pi diameter given is 8 centimeter. We convert to meter, which is 1 to 0.08. Okay, 0.08 squared over 4 plus m.2 given here is 4 kilogram plus density, which is 1000 multiplied with volume flow rate at 3, which is 0.008. Okay, simplify the equation. Finally, you will get dm over dt is equal to 38.27 kilogram per second. That is the final answer.